Hello and welcome to the 12th part of the tutorial on writing your operating system. And okay, today is a big one. Okay, now in this video we will go to the graphics mode. And okay, we won't go into a great graphics mode, just some VGA graphics, 320 times 200 pixels with 256 colors. So that's nothing special, but it sets, it gives us at least something that we can work on to build a desktop and a GUI framework and stuff. So, one problem that we have right now is we still don't have any dynamic memory management. So that is why in the enumeration of the devices for the peripheral component interconnect, we cannot instantiate the driver dynamically. But we have one advantage, namely the VGA is relatively simple. It's quite similar to how it works with the text mode. There's just some certain memory locations and you write stuff there and then this is drawn on the screen. But you need to set the graphics card to graphics mode so that it actually does that and doesn't look for the text at, what was the offset, 0x, what was it, B8000 or what it was. So it's similar, but we need to change the mode. And changing the mode is really hard because when you Google this, when I went into this, I Googled for a long time for an answer, and I was actually I almost quit it because you just don't find anything good, because almost all websites that talk about graphics mode and VGA graphics just say, well, use the interrupt 13H, hexadecimal 13. In C++, this 13H I think is basic syntax, I think. So, interrupt 19 or hexadecimal 13. And almost all tutorials, I don't know, I've read dozens of tutorials and they all tell you just call interrupt hexadecimal 13 and it doesn't work. This is how you did it in the DOS times, and I guess that Windows has some compatibility for this interrupt. So when you call that interrupt in a Windows program, I guess Windows just emulates the behavior in a way. But when you're writing your own operating system, this doesn't work because interrupt hexadecimal 13 is a BIOS interrupt. Okay, that's not. We had situations where the operating system did stuff for us when we are working inside an operating system, and we cannot use these things when we are outside of the operating system. But that's not the problem here. If you remember, we had the situation at the boot process of the computer, the firmware is loaded, and then the firmware loads the bootloader, and the bootloader loads the kernel, right? So here you have the firmware, the BIOS, then you have the bootloader, and then you have the kernel. And this interrupt hexadecimal 13 is actually a BIOS interrupt. So this might actually work even if we don't have a Windows kernel or a Linux kernel to rely on. But the problem is grub puts us in 32-bit mode, even before our kernel starts. And these VESA BIOS extension interrupts, like this one, they are deactivated in 32-bit mode. So what you could do is you could go back to a 16-bit mode, and then you would have, then you would be able to use that interrupt. But I don't even know how to go to 64-bit mode, and going backwards, I don't want to do that. So this isn't what I want to do. So if you don't use the BIOS interrupt to switch the mode, well, then you need to talk to the graphics card directly and tell it to go into graphics mode directly. And I want to point you to a source code on osdev.org. Here at this address. There's a lot of code here, and in particular you have these these sequences here for text mode 90 times 60 characters, graphics mode 640 times 480 times 2 colors, or 2-bit, I'm not sure, no, 2 colors. So here you have different initialization codes for different resolutions and color depths. And that is really just what we have to do. We just have to send these codes to the graphics cards to set the mode. Okay. Now one thing, the design of the VGA graphics is really, really bad. So when they came up with this stuff, they really weren't thinking too far into the future. So for small resolutions, you already exceed the capacity of the RAM. You know, I told you in the text mode you have this particular offset, and what you write there is put on the screen. And with the graphics mode, there's also a certain offset, and the colors that you put there correspond to the pixels on the screen. But yeah, this the size of this memory location is just too small. I don't know exactly from the top of my head what the size actually is, but since it is already too small for very small resolutions and color depth, they came up with strange ways of circumventing the problem with so-called bank switching and also so they just have multiple different locations for the different resolutions. So if the resolution is too large, then you have multiple of these memory locations, and you need to know where to write your data now. And this is quite tedious. As I said, I think this is really bad design. They just weren't thinking too much about having higher resolutions back then. But okay, so this is the way it is. What I wanted to say is, the VGA is very similar in the way that these memory locations are fixed. So you don't need to really communicate with the PCI controller and stuff to find this out. So because of this, we don't really need dynamic memory management at this point, right? We can handle this just the way we handled the text mode. We'll just have a driver, and we can instantiate it in the kernel CPP. I mean, it's not really a good design, and I think it's a better idea to have a mock-up that hides this functionality in the enumeration of the PCI devices, but whatever. Let's just start with sending these codes to the graphics card so that we get into graphics mode. Okay. Include drivers. Okay, so the VGA has a lot of ports. Let's see, 11 ports. This is madness, but okay. Okay. Okay, we have one port for miscellaneous stuff, one for the cathode ray tube controller, index and data. Cathode ray tube controller. By the way, when you do graphics programming inside Windows or Linux or whatever, you have an operating system protecting you from doing bad things, you know. But if you you are writing your own operating system. There's nothing that protects you from sending wrong data to the graphics card and the monitor, and it could potentially really break your hardware when you send the wrong data. And I mean, VGA is pretty standardized, but I don't know. I'm not taking any responsibility if anything breaks on your hardware, or in theory, it could even happen that your monitor explodes. And you might get injured or maybe even die. I don't think that that this is a realistic scenario in times of TFT monitors and stuff. I think this is really that was a concern with CRT monitors. But I've warned you, okay? You're doing this on your own responsibility. Sequencer index port. Attribute controller index port. And this is a little bit different than the other ports. We don't have a data port. We don't have index and data. We have index, read, write, and reset port. Okay. Constructor, destructor. Okay, then we will have a method to set the mode. Width, height, and depth. But we'll also have a method which tells us if a certain mode is even supported. Okay. Then we will have a method which sends these initialization codes to the corresponding ports. So, like this. Then we will have a method which gives us the location of the memory. Look, you know, this frame buffer segments. You know, if we need a method that gives us the correct offset for the segment that we want to use. So, like this. And this is needed for the method put pixel. Yeah, here I will do this in a more abstract way. So I will have a method put pixel which accepts a 24-bit color code, red, green, blue. So this method is supposed to put this color to this coordinate. Okay. Okay, but yeah, the VGA we will be using an 8-bit version for now. So actually we cannot actually set a color like this. So the put pixel method down here is supposed to get an index. The 8-bit color modes use basically a table of 256 entries. Of different colors, and then here you just select an index in that table. Okay, so the put pixel method actually needs to get this color index for a certain color. Get color index for an RGB color. Okay, so the put pixel method down here is supposed to call get color index to get a sane index for this color. I mean, we could give it too many different colors here. So the driver is supposed to hide away the fact that it cannot actually represent this many colors. So we might have only one light blue, and if we want to set one light blue or a different light blue, they might get drawn as the same light blue in the end, but this is supposed to be hidden from all the things that draw on the screen. Okay, the objects that draw on the screen are not supposed to know that you have only 8-bit color depth in behind this. Okay. So, Okay. Okay, now we initialize the different ports. Okay. So the miscellaneous port, that is port number 0x3C2. The cathode ray tube controller index port is 0x3D4. Data port is 3D5. Sequencer index is 3C4. Sequencer data port is 3C5. Graphics controller is 3CE and 3CF. Attribute controllers is 3C0, and the write port is also 3C0. C1 and 3DA. Okay. Okay, for now we will just implement the mode 320 times 200 and 8-bit color depth. Okay, so. Okay, so this is the only mode that we support right now. And in the set mode, here we basically just take this from this file here in osdev.org, this one here. So the 320 times 200 times 256. Okay. And we just we just pass this to the write registers method. So. And then we return true. So it should have worked at this point that we have set the mode. But if the mode is not supported, so if we try to set the mode to an unsupported mode, then we just return false. Like this. Okay. Now, how do we set, what does this write registers method do? It just writes this data to the miscellaneous port, this to the sequencer, this to the cathode ray tube controller, graphics controller, and attribute controller. So, okay. So we get this pointer to the register entries here. And then we just write the first one to the miscellaneous port and increase this pointer, because the data that we had in the miscellaneous we don't need anymore, so we can basically just discard the old pointer and have it now point to the next memory location. Then we have 5 values that we write to the sequencer. And this is quite similar in the next for the next ports also. So you first write the index to the index port and then the data to the data port. So sequencer index port, write I. Wait, this is supposed to be an 8-bit integer. So first we say, where do we want to write the data, and then what do we want to write there to that index. Okay. So this is for the miscellaneous, this is for the sequencer. Okay, for the cathode ray tube controller, there we have 25 values which we send. Like this. For the graphics controller, there we have 9 values. And the attribute controller. There we have 21 values. Attribute controller index part. Attribute controller. Here we have a little difference. So we write to the index port the I and to the write port the data, but first we need to reset the attribute controller before we send data. So attribute controller reset port dot read is how we do that. Okay. Now one more thing is, we need to do something like some mutual exclusion. So the cathode ray tube controller, because this is, I think this has to do with the fact that the cathode ray can blow up if you send the wrong data there. So you need to unlock it, send data there, and then lock it again. I think this is a security feature. CRTC index port dot write 0x03. So we read the old value, do a bitwise OR with the number 0x80, and write the result. So basically we are just setting the first bit of this to 1. Right? We get the old value, set the first bit to 1 with this, and write it back to that index. And here, for the 11th, index, or 17th actually, we set the first bit to 0. like this. Okay. Yes. Okay. Now, if the data that we get, which we send to the CRTC, I mean, we are overwriting these values again in this loop down here, right? So, so this would actually unlock the controller again, or no, it would lock the controller again if we got wrong data in these registers here. So So in the register that is written to 0x03, we also set the first bit to 1. And in the register that is written to 0x11, we set the first bit to 0. Just to make sure that we don't accidentally overwrite this again. Okay. And when we are finished, attribute controller reset port.read. So we reset the attribute controller again. And write a 0x20 to the attribute controller index port. Okay. Okay, what do we do? What do we have now? So the ports are initialized. We can write the registers. And we can set the mode. Okay, and down here, this putPixel method down here will just call the other putPixel method with the same x and y, but with the getColorIndex for the RGB value. Okay, for now, I will just do a little mock-up here. If R is equal to 0, green is equal to 0, and blue is equal to 0x8, just return color 0x01. So this is just the index. I think VirtualBox has this as a default setting, I think. Although I've run this on actual hardware also, and it also worked, so it's probably standardized, I guess. So we get the color index and pass it to putPixel. And putPixel works like this. So it asks this get frame buffer segment where to put the pixel. So we get the current frame buffer segment and add, we haven't stored the width and the height anywhere, so I will hard code this to 320. Times y plus x. And at this address, we put the color index. Like this. Okay. Whew. Now the last thing we need here is the get frame buffer segment. And this works like this. We are looking to the index number 6 for the in the graphics controller. So the segment number we get from the data port. Okay, the code that I have here is a bit ugly. I think I will do it a little bit differently. I'll shift this by 2, so we are only interested in the bits number 3 and 4. So we just remove the last 2 bits. And then we take the bitwise AND with the numbers 3, so that all the other bits are killed. Okay, now if this is a 0, then we need to write our data to the memory location. Okay, this is a bit odd. Just Just 0, okay. Bit strange, but okay, I will also put a default here. I think the compiler complains if you don't have a default value here. So 0xa 0000. That's in case 1. 0xb 0000 is for case 2, and case 3 is 0xb 8000. Okay. Yes, I think this should be it. But you know what? I will just I will make this pixel with a color index. I will make this public also for now. It shouldn't be in the long run, but for now I will just do this. Okay. Okay, in the make file we now need object drivers VGA.o. And in the kernel have a VGA here. Okay. And then have VGA.set mode 320 times 200 times 8 bits. And then let's just draw a blue rectangle on the screen. And then as the color that we set, we only had this 0x00, 0x00, 0x A8. Right, this was the only color that we had. Okay, let's see if this works. Okay. Okay, it looks crappy. This isn't what we wanted. But at least it does something, you know. It's not a bad sign. Okay, I mixed up this the ports here. So the read port is 3C1 and the write port is 3C0. Okay, let's see if this works now. Okay, still not working. Okay, so I found the mistakes that I made. Yeah, it just shows that you really need to be sure how many bytes you use. Okay, so the problem was that I was using uint 8t for y and x here, and 320 is outside of the representable numbers for an uint 8t. So actually the compiler should have told me an error message there, I think. But so make this int 32, both of them. Okay, here we instantiate it, set the mode, and iterate over the pixels and set them to blue. So make clean, make run. And bam, the screen is blue. Yes. Okay, now I've installed it on my actual machine. Rebooting. My operating system. And you see, yeah, we have a blue screen. Okay, yeah, this is not a blue screen. We have now put the actual hardware in graphics mode and drawn a blue screen on everything. So yeah, this also works on the actual hardware, and I think this is really an awesome feeling. One of the biggest milestones that you will have in writing your own operating system. So yeah, so there you have it. You can also run this on your actual hardware. Okay. So, yeah, this wasn't that hard, I think. I mean, you need to set the mode, and then you just need to write the pixels in the right positions. But I think this is sufficient for today. So next time we will talk about GUI frameworks, so that we can actually build a desktop on top of this graphics mode now. Yeah, so yeah, tune in next time. Don't forget to subscribe, and also hit like if you liked the video. Yeah, so see you next time. Bye.